Here we have practice problem 6.13, and we're given A through D down here, which are following multi-step reactions. So we're going to take a look here and identify at each of the arrows, right? We can identify a arrow pushing pattern. So if you remember, there are four common arrow pushing patterns. We have proton transfers, nucleophilic attacks, loss of leaving group, and rearrangements. So let's take a look here at example A. And the first arrows indicate a nucleophilic attack. So we can identify this as a nucleophilic attack. And specifically, our pi bond here is acting as a nucleophile. And due to inductive effects here, we see that our sulfur atom is acting as an electrophile. So we have nucleophilic attack in our first step in this multi-step reaction. And then we see two arrows again here with this next reaction step, which would be proton transfer. So we see the water molecule here. The lone pair is where the arrow tail starts. The head goes over to this proton, and the result is a proton transfer. So we end up with hydronium, and this becomes a double bond here when the electrons involved in this carbon-hydrogen bond move into the ring. And we'll see, so this is a proton transfer. And then we have hydronium and this site here, right? The tail end of this arrow starts on this lone pair. The head of the arrow grabs this proton, and then we see this bonding pair moves to be a lone pair on water. So again, we see another proton transfer happen. All right, so the three steps that we see in example A are nucleophilic attack, proton transfer, and then another proton transfer. In example B, we have, again, a lone pair on an oxygen, where the tail of the arrow is, and then the head on this proton, this hydrogen that has been exaggerated here. So this bond between the carbon and the hydrogen moves in to the end of this molecule, and we can see now there's a lone pair on that carbon. So this first arrow pushing pattern that we see here would be a proton transfer. Right. So then we move to this lone pair that's left on the carbon, then acts as a nucleophilic site, right, with this negative charge on this carbon. And this molecule then reacts with itself due to induction here on this electron withdrawing group, the oxygen atom. What results is an electrophile, right? A partially positive site on that carbon there. So this would be a nucleophilic attack that we see here at these arrows. And then last, we see loss of a leaving group. So specifically over the arrow here, we see minus RO. So what happens is we have the movement of a lone pair from the oxygen atom to form a double bond here. And that kicks out, right? We already have a full octet in that carbon there, so we can't violate the octet rule. So that kicks out these electrons involved in the bond on this alkoxide group here, this RO, and that serves as our leaving group here. So we see loss of leaving group. And then down here we have examples C and D. So the first step in this mechanism C, we see a proton transfer. So that leaves a negative charge at this carbon here, right? This extra lone pair that wasn't there. And then we see in the second step, um, we see this lone pair move and form this uh, triple bond. And that triggers a movement of electrons from this bond here, this carbon-hydrogen bond has to be broken. And we see those electrons move up onto that chlorine, and then our loss of leaving group here is our chloride ion. That's our leaving group, the chloride ion. So then we have this triple bond that results, and we see our hydroxide ion here acting as a nucleophile in this case. And the tail of the arrow is where the electrons begin, right? We have this nucleophilic attack on either side, really, of the triple bond. Let's actually get rid of some of that there. Oop. So we have this nucleophilic attack from the hydroxide ion, and then some electrons from that triple bond move back onto this carbon here. So we end up with the hydroxide ion adding to the molecule and a lone pair. So the next step here, or rather this step here was a, right, this was our nucleophile, so we had a nucleophilic attack before we get ahead of ourselves. And then this last step here, we see this lone pair grabbing this proton, and then the bond that was involved in this water molecule, those electrons move on to the oxygen, so we end up with a hydroxide group and the proton added right here. So we had a proton transfer in this step. All right, the last example, I'll move a little quicker. We see this lone pair grabbing this proton, and the result of a proton transfer is seen here, right? We have this deprotonated site. Then we see in this second step a nucleophilic attack. And we see our last arrow here, right? This lone pair is grabbing this proton. So this is a proton transfer. All right, so that's everything for question 6.13. We'll continue with 6.14 next time.